So something that actually was more like an experimentation. We were curious to see if pan-sharpening could be used in planetary sciences. What's pan-sharpening? So a lot of you probably will have never heard about this word, but it's very used in some particular ambits of images ambit of Earth ambits because it's now a field of study is actually a family of methods that started the idea from something like 40 years ago. The idea was to combine the spectral information from multispectral or hyperspectral data with the higher resolution of a panchromatic image. That's the origin of the name pan-sharpening. So use panchromatic to actually sharpen a spectral information. What does it mean? That at the end, the pan-sharpening algorithm, the pan-sharpening methods you used are finalized to actually have a method, data, an image that you cannot have otherwise. That is an image with both high spectral and high spatial resolution. And that's something that actually you cannot have in other methods. For a simple reason, for physical reasons, for the fact that you are fractioning the spectral component of the light, both in a small area and in a small part of the spectrum. That's not something that even today with our technologies we can do. So this idea started. Now we are talking about 40 years of developing. So a lot of things happened, a lot of things was born, and most of them remained in the ambit of theory, just in the ambit to be used as a we can do it study. A study with some little tests, very small images, benchmarking, but not real case study. What we started 1 year ago is to actually see if some of these methods can be used and adapted to our images. The pan from PANCO is actually from pan-sharpening. The co is due to a limitation or assumption, your decision, that pan-sharpening needs. Pan-sharpening needs the alignment of images. When they started with this idea, they was thinking about sensor that was on the same spacecraft or images that are part of the same instrument. So they imagined images already aligned. But that's not something that we have usually in planetary sciences. That's very difficult to achieve. And most of the time you made it manually. I don't know, probably most of the people here will already worked with GIS software and or the rest of it you will see it in the next days. Georeferencing is the part of aligning two different images that can have very different geometrical characteristic and also illumination conditions. That's not something simple, and you align them by choosing points between the two images manually, and that's very long, honestly very boring process that we cannot make otherwise in usual software, in usual GIS. With PANCO, we are trying to make a different approach and also to make it simple and feasible for all the application, not only pan-sharpening. This approach is based on the fact that the search of points can be in a part automatized, and we use a computer vision algorithm like shift in this case, the scalar invariant feature transform, that can actually use what you search in an image. Let's imagine you have two images to align and you have to search similar points. So what you can do is search for patterns, something very, very recognizable, like a crater, or like a color change, a strange feature, something that actually seems to use something similar. And the shift algorithm, that is the one we used, works in the same way. So it searches for patterns at different scale and with different contrast. With this method, with this approach, we found more points that we actually do usually when we do it manually. We are not talking more than tens, but more in the range of hundreds to thousand points. What does it mean? With all these points, at this point, we can match the geometry of the two images, defining an homographic projection. If you don't know what is an homographic projection, just imagine to see a part of the image or a piece of surface from different perspective. With an homographic projection, you are changing the perspective of the images. So if two images taken from different instruments or sensors are seen from different part, now you can match it with an homographic projection. And that's the first part of the moment. I try to use my, okay. That's the first step of the alignment. Going to the second step, when you use homographic projection, you treat images like a plane. You then have to refine a little bit the projection, just in the part where the topography is a little bit more aggressive, because if you use the image as a plane, you cannot have the certainty that these aggressive features like crest are the same, because can be a little bit shifted. So our approach means that you don't need to find all the points. You need just to have the first automatic part and then the refining manual. This means also that georeferencing to images in PANCO is not more a matter of tens of minutes or hours, but minutes, 5 to 10 minutes, depending on our experience. And in this way, we can be even more precise than we actually do when we are inaccurate operators that actually search it by hands. As you can see on the graph on the right, with this approach, we arrive usually to less than 1 pixel of precision when you to the final alignment, sorry, less than 1 pixel. Obviously, we are talking about the pixel of the lower resolution image, the spectral one. So in this case, that was done with cassis images and arrays images. That means less than 1 cassis pixel. If you don't know what cassis is, don't worry about it. I will talk about it. So, generally speaking, PANCO, our objectives. We started from experimentation. Now we are doing it like free and open source software for the entire scientific community. That means that you can actually download the software, change the software, modify it, or make it your own just for the fact that it's open source. So you can take the code of that. In future, we'll have also a graphical interface, then it's a little bit more easy to use, but also in this phase is not so complex. I will talk about it. The second objective is the fact that we'll have a more efficient and accurate method of alignment of images, starting from the part I already talked about. And also a toolkit of methods, because like I said to you, pan-sharpening is not one method, it's a lot of methods that comprehend different algorithms. So the operator can actually choose what is better for his own applications. And also methods that are capable of multi-spectral images or for hyperspectral datasets, hyperspectral cubes. We want to simplify this choice to operators, so we are doing a series of studies that are dedicated to see the performance of the methods in real case studies. Starting from the first one that was done with the Cassis color images, that is a instrument on board on the ExoMars trace gas orbiter that is operative since 2016 now, and is giving us beautiful images, color images at 4.5 meters pixel. The panchromatic one for us is Iris. Iris is probably the most famous of the sensors that we have on Mars now, because it's the one that arrived to the most beautiful resolution we have, that is just 25 centimeters. If you make a little calculations, we pass from the resolution of Cassis, 4.5 meters, to resolution of Iris. So we have an 18 times enhancement in spatial resolution. We already published this part of the study, so if you're interested in the details, more that I can do it today, I can tell today, please use the QR code or the link to arrive to the publication. The second study that is actually ongoing is the fact that some modern methods are capable of using or managing hyperspectral data. So we are trying to make a similar enhancement up to 4 to 8, depending of the original resolution enhancement, but not only for 3 or 4 bands, but for the whole dataset of CRISM bands. CRISM is the other spectral imager that we have on the same mission of IRIS, the MRO, the Mars Reconnaissance Orbiter. And I will talk also about the results of this. The first objective was the fact to be open source. So this is the link to PANCO suite. I'm leaving to you this information so you can actually connect if you want to see the software for itself. I hope some of you will actually use it for your own studies. The way of usage of PANCO is very simple. For now, it was born like Python functions. So you can actually use it by standalone. So use it by putting your information, the images path, in the lower part of the scripts. For every script you want, for every method you want, is the same concept. Or if you're a little bit more advanced in programming, you can actually use it in your application. Like you see on the right, you can import the single method in as a function and as a module, and so you can use the function. Okay. Up today, we arrived to something like 15 methods already available on PANCO. The black one are the ones that are already been tested in some studies, and also they are capable of multispectral imaging. The blue one are the newest one we are actually testing right now. You don't find it right now, this one, but the study is near to submission, so you will probably have it really soon. And they are capable of any number of bands you want. As you can see from the image to the right part of the slide, different algorithm means also different results. In some of the cases, the algorithm tends to enhance the colors or pop up colors, like the very yellowy images we have, like D, E, F, or other one are meant to be very precise and accurate to maintain the spectral capabilities, spectral information, like the E, J, and K. They are very much oriented to a more spectral analysis study. Some of these one, as you can see from the results that I will talk very soon, are more organized to be both. So era a compromise. This. I was talking about these satellites. These are the spectral properties of the satellite, the instruments we used. The Cassis has 4 bands, very pretty much with the same largeness, so they are same width, spectral width, so they are centered in blue-green, the first one. Then we have the pan that it's actually going to the green part of the spectrum, to the red part of the spectrum, and the whole red, not centered in 700 but in 800, so it's a red to near band. And then we have a big part of infrared, so we have the near infrared band. For fire eyes, we actually used only the red band, because also if you see the spectral range is pretty big. It's centered at actually red, so it's 700 nanometers, but it's covering a big part. So it's more a panchromatic band than actually a red one. The Chris bands are near 500 and cover all the spectral range from everything the Cassis sees and way more in the infrared and shortwave infrared ambit. So it arrives actually to micrometers, not only nanometers ambit. To be sure about the results, we actually selected images from a big part of Mars, taking different geological condition, different illumination condition, different geometry of images. What does it mean? That we actually see things very different one part of another of Mars. We see color differences, and we see things that we can discriminate, so we can see if these aspects can actually be part of the results, if they influence the results in a good or bad way. And coming to results. This is a first example of what does it mean to have a 18 level of enhancement. This on the right, the A image, is the original Cassis, a detail, a very small detail. This on the right is the image pan-sharpened, so the Cassis pan-sharpened. As you can see, a lot of structure, geological structure, are popping out, like this beautiful layering, these ridges. And also, if you are very good or your screen is big, as you can see, not only this crater is popping out, but also the little boulders inside. This is not a game changer. This is not something you cannot have in other way. The iRise was already there, but what we are trying to create is to combine the information to have something that is a little new and something that actually can help a lot of part of the studies, geomorphological studies, spectral studies, and so on. Spectral indicators and also structural indicators have been used for these studies. So we don't actually make just objective observation, subjective observation, but we have made use of also of indexes that gives us some information about the results. We are very pleased to see that some of the methods actually arrive to indicators to a level of indexes that are not ideal, but something like that, or very close to be ideal. What does it mean? An ideal pan-sharpened image is the one that actually maintains all the spectral information, so the spectra remain undeformed. Use image spectral as the part of the spectrum that compose the single pixels. But from the structural point of view, the original one is no more important. For the structural point of view, the perfect pan-sharpening is the one that acquires all the details from the panchromatic part of the process. So in our analysis, we split the two analyses and we made spectral indicators like the SAM and root mean square error and ERGAS, that is actually French for Erreur relative globale dimensionnelle de synthèse. I will never repeat it. This again is actually a cumulative indicator of the changes in reflectance of the spectrum. In the structural point of view, we used some modern indicator like the structural similarity index and the universal quality index. In these cases, the deformation of the spectrum, the best is 0. So if you see that a lot of methods actually arrive to something that is near 0, or the sum that means the degree of deformation of the spectrum actually arrives to less than 0.5 degrees for most of the methods. For the structural point of view, you want all the information of the new one, so it's 1. If it's equal, it means that the ideal result is 1, like in the Gram-Schmidt phase, this one, and this one. Okay. We choose an iRise also because there is another possibility to our analysis. iRise has the two little bands. I have also two little bands. They are centered in the blue-green part and in the infrared part. It's not the similar of Cassis actually, so we have some difference, some big difference in this. But also, and also cover a very narrow part of the image, just 1.2 kilometers at the equator. So iRise is not actually a color imager. It's just some more information for the central part. But for our analysis, it's an interesting example because we can compare a sensor that is already at color for small pieces, but it's already a color part. As you can see, starting from the A, that is the original Cassis, B is the original iRise using all the 3 bands. What you can see that actually using different pan-sharpening algorithm, we arrive to something that is very, very similar to the iRise colors. Not in the number point of view because it are different bands, but from the point of view of subjective quality estimation, it's pretty close. So we can say with a lot of certainty that these images are to be considered not equal but comparable. Coming to the hyperspectral part of the tools, the study is already going, and as you can see from these preliminary results, we have a deformation of the spectrum, also in this case, that is very little. We take 3 different rows in these 2 images as an example, and we made the average spectrum. As you can see, the same spectral, so the same spectral information inside of the single pixels remain the same. You can see the same absorption bands. You can see all the overall shape is maintained. Also, index indicators means the same, gives us a lot of similar information as for the CASIS studies, for the previous studies. We have a deformation of the spectrum that is also in this way, also in this part of the study, under 0.5 degrees. In most of the cases, under 0.05 degrees. And also the cumulative, so summed for all the bands, on average, it's very close to zero. We have less than 15. That's usually a very, very good value for ARCAS in a spectral ambit. The structural part is not totally close to 1 like before, but we have something that is pretty close. We arrive to more than 0.65. That is usually a limit for the structural similarity index to show similar image, or better, the same image but with error. So we also in the perspectral ambit, the first results we are having are very good. And so we have a little bit of hope to be also this part can be something that we'll use in scientific studies in future. In this part of the study, so in the hyperspectral part, we decided not to be just relying on spectral indexes like the one I talked before, but also we want geologists or physicists to actually use the data to make some spectral analysis. In this case, this is an image in the northern Hellas of Mars, and we have that the spectrum is very similar, and we still see some very interesting features in our spectra. In this case, we have the very large and beautiful absorption of the olivine, very typical of olivine minerals, like this one. And it's totally the same that the original, this one on the right. Or for small absorption band like pyroxenes, we see that we maintain the perfect absorption in different parts. So also in this case, also in the interpretation part, our preliminary results actually shows that hyperspectral methods are capable of having good results. Coming to a very more practical part of the pan-sharpening of the tools. Using the whole images or using or time to process big part of the images is something we actually don't advise for a simple reason. It's resource hungry. It's a lot resource hungry. So for your usage, so if you're starting now to explore pan-sharpening, it's better to clip images a little bit smaller. Don't take, please, the whole image. It will be a very difficult process for you. It's better to start from clip of images. These are the RAM and time usage we have on our workstation. Using the whole images, we always have time of processing. There are more than 10 minutes. And also we arrive to peak of RAM consumption. They are very high. In some cases, we reached 40 gigabytes of RAM. So that's just, I close with just with an advice. Please try to use PANCO if you want, if you're interested, but make it on small images for now, or clip images and make it 2 or 3 times.